In this video, I'm going to introduce Hopfield Nets. Together with backpropagation, these were one of the main reasons for the resurgence of interest in neural networks in the 1980s. Hopfield networks are beautifully simple devices that can be used for storing memories as distributed patterns of activity. We're now going to learn about a very different kind of model from a feed-forward neural net. These are sometimes called energy-based models because their properties derive from a global energy function. So a Hopfield net is one of the simplest kinds of energy-based model. It's composed of binary threshold units with recurrent connections between them. In general, if you have networks of nonlinear units with recurrent connections, they're very hard to analyze. They can behave in many different ways. They can settle to a stable state, they can oscillate, they can even be chaotic, which means that unless you know their starting state with infinite precision, you can't predict the state they'll be in very far into the future. Fortunately, John Hopfield and various other groups like Stephen Grossberg's group realized that if the connections are symmetric, there's a global energy function. Each binary configuration of the whole network has an energy. And so what I mean by binary configuration is an assignment of binary values to each neuron in the network. So every neuron has a particular binary value in a configuration. The thing that Hopfield realized is that if you set up the right energy function, the binary threshold decision rule is actually causing the network to go downhill in energy. And if you keep applying that rule, it'll end up in an energy minimum. So everything's controlled by the energy function. The global energy of a configuration is the sum of a number of local contributions, and the main contributions have the form of the product of one connection weight with the binary states of two neurons. So the energy function looks like this. Energy is bad, so low energy is good, and that's what those minus signs are doing in there. If you look at the main term here, it has a weight, which is the symmetric connection strength between two neurons, and it has the activities of the two connected neurons. So SI is a binary variable that has values of 1 or 0, or in another kind of Hopfield net, it has values of 1 or minus 1. In addition to that quadratic term that involves the states of two units, there's also a bias term that only involves the state of individual units. The quadratic energy function makes it possible for each unit to compute locally how changing its state will change the global energy. So we first need to define the energy gap. The energy gap for a unit I is the difference in the global energy of the whole configuration depending on whether or not I is on. So the energy gap we're going to actually define as the difference between the energy when I is off and the energy when I is on. And that difference is just what's being computed by the binary threshold decision rule. So if you look at the equation for the energy and you differentiate it with respect to the state of the ith unit, it's a funny thing to do because it's a binary variable. But if you differentiate it, you'll see you get the binary threshold decision rule, but without the minus sign, because that's for going downhill in energy. So by following the binary threshold decision rule, a Hopfield net will go downhill in its global energy. One way to find an energy minimum in a Hopfield net is to start from a random state and then update the units one at a time in random order. So we're doing a sequential update. And for each unit that you pick, you compute whichever of its two states gives the lowest global energy and you put it in that state, independent of what state it was previously in. That's equivalent to saying you just use the binary threshold decision rule. So let's look at a little example for the net on the right. We'll start with a random global state. This was a carefully selected random state. and that has an energy of -3, or a goodness of 3. It's easier to think about negative energies, which I'll call goodnesses. There aren't any biases here, so to compute the goodness, you just look at all pairs of units that are on and add in the weight between them. And in this configuration, there's only one pair of units that's active, and that has a weight of 3, so we get a goodness of 3. Now let's start probing the units. Let's pick a unit at random, like that one, and ask what state should that be in, given the current states of all the other units. So if we look at the total input to that, it gets an input of 1 times -4, plus 0 times 3, plus another 0 times 3. So it gets a total input of -4. That's below 0, so we turn it off, i.e. it stays in the off state. Now let's probe another unit. If we look at this unit, again, it gets a total input of 1 times 3 plus -1 times 0. So it gets a total input of 3, so the binary threshold decision rule will make it turn on. Let's probe one more unit. This unit's more interesting. It's getting an input of 1 times 2 plus 1 times -1 plus 0 times 3 plus 0 times -1. So that's a total input of 1, so it will now turn on. Previously it was off, and so when it turns on, the global energy changes. We now have a global energy of -4, or a goodness of 4, and that's a local energy minimum. If you now try probing any of the units, you'll see that they don't want to change their current state. The net is settled to a minimum. However, the minimum it's settled to is not the deepest energy minimum. It's just one of 2 minima that this net has. The deepest energy minimum is shown on the right here, and it's when the other triangle of units that support each other is on. That has a goodness of 3 plus 3 plus -1 is 5. So that's a slightly better energy minimum. If you look at that net, you can see the net's composed of these two triangles, in which the units mostly support each other, although there's a bit of disagreement at the bottom. And each of those triangles mostly hates the other triangle, via that connection at the top. The triangle on the left differs from the one on the right by having a weight of 2 where the other one has a weight of 3, so the triangle on the right will give you the deepest minimum. So if you ask, why do the decisions need to be sequential in a Hopfield net? The problem is that if units make simultaneous decisions, they could each think they were reducing the energy, but actually the energy could go up. With simultaneous parallel updating, we can get oscillations, which always have a period of 2. So here's a little network where the units have biases of +5 and a weight between them of -100. So when both units are off, the next parallel step, if we update them both at the same time, will turn both units on, because they each think they can improve things via the bias term. But as soon as you do that, you get this -100, and so you've actually made things much worse. So then at the next parallel step, both units will turn off again. If we do the updates in parallel but with random timing, in other words, we don't wait for one update to communicate the state to everybody before we consider another update, but we do wait for random lengths of time between doing updates of a given unit, then those random timings will often destroy these biphasic oscillations. That means that the idea that the updates have to be sequential isn't quite as bad as it seems from a biological perspective. Now what Hopfield suggested was that we could make use of this kind of energy-based model that settles to a minimum of its energy for storing memories. So he had a very influential paper in 1982 that proposed that memories could be energy minima of a neural net with symmetric weights. The binary threshold decision rule can then take partial memories and clean them up into full memories. So the memory could be corrupted by part of it being wrong, or part of it could just be undecided, and we can use the net to fill out the memory. The idea of memories as energy minima goes back a long way. The first example I know of is in a book called Principles of Literary Criticism by I.A. Richards, where he proposes that memories are like a large crystal that can sit on different faces. Using energy minima to represent memories gives a content-addressable memory, as Hopfield realised, so that you can access an item just by knowing part of its content. I can tell you a few properties of something. That'll set the states of some of the neurons in the net, and if you've put the other neurons in random states and now go around applying the binary threshold rule, with a bit of luck you'll fill out that memory to be some stored item that you know about. When Hopfield Nets were proposed in 1982, that was a very interesting property. 1982 was 16 years before Google. Now that we have Google, we regard this as perfectly obvious. Another property of Hopfield Nets that's biologically interesting is they're robust against hardware damage. You can remove a few of the units in the net, and unlike the central processor of your computer, everything will still work fine. Psychologists have a nice analogy for this kind of memory. It's like reconstructing a dinosaur from just a few of its bones, because you know something about how the bones are meant to fit together. So the weights in the network give you information about how states of neurons fit together, and now given the states of a few neurons, I can fill out the whole state to recover a whole memory. The storage rule for memories in a Hopfield net is very simple. The idea is, if we use activities of 1 and -1, that we can store a binary state vector by just incrementing the weights between any two units by the product of their activities. So it's a very simple rule shown on the right. One nice thing about this rule is that you just go through the data once and you're done. So it really is a genuine online rule. That's because it's not error-driven. You're not comparing what you would have predicted with what the right answer is, and then making small adjustments. The fact that it's not an error correction rule is both its strength and its weakness. It means it can be online, but as we'll see later, it also means it's not a very efficient way to store things. We can also have biases, and as usual, we treat the biases as weights from a permanently on unit. If you want to use states of 0 and 1 for units, which is what we'll use later, the update rule is only slightly more complicated. In this video, I'm going to talk about the storage capacity of Hopfield nets. Their ability to store a lot of memories is limited by what are called spurious memories. These occur when two nearby energy minima combine to make a new minimum in the wrong place. Attempts to remove these spurious minima eventually led to a very interesting way of doing learning in things considerably more complicated than a basic Hopfield net. At the end of the video, I'll also talk about a curious historical rediscovery where the physicists trying to increase the capacity of Hopfield nets rediscovered the perceptron convergence procedure. After Hopfield invented Hopfield nets as memory storage devices, the field became obsessed by the storage capacity of a Hopfield net. Using Hopfield's storage rule for a totally connected net, the capacity is about 0.15 n memories. That is, if you have n binary threshold units, the number of memories you can store is about 0.15 n before memories start getting confused with one another. So that's the number you can store and still hope to retrieve them sensibly. Each memory is a random configuration of the n units, so it has n bits of information in it. And so the total information being stored in a Hopfield net is about 0.15 n squared bits. This doesn't make efficient use of the bits that are required to store the weights. In other words, if you look at how many bits the computer is using to store the weights, it's using well over 0.15 n squared bits to store the weights. And therefore, this kind of distributed memory in local energy minima is not making efficient use of the bits in the computer. We can analyse how many bits we should be able to store if we were making efficient use of the bits in the computer. There's n squared weights and biases in the net, and after storing m memories, each connection weight has an integer value in the range minus m to m. That's because we increase it by 1 or decrease it by 1 each time we store a memory, assuming that we use states of minus 1 and 1. Now, of course, not all values will be equiprobable, so we could compress that information, but ignoring that, the number of bits it would take us to store a connection weight in the naive way is log 2m plus 1, because that's the number of alternative connection weights, and that's a log to the base 2. And so the total number of bits of computer memory that we use is of the order of n squared log 2m plus 1. So notice that that scales logarithmically with m, whereas if you store things in the way Hopfield suggests, you get this constant 0.15 instead of something that scales logarithmically. So we're not so worried about the fact that the constant is a lot less than 2. What we're worried about is this logarithmic scaling. That shows we ought to be able to do something better. If we ask what limits the capacity of a Hopfield net, what is it that causes it to break down, then it's merging of energy minima. So each time we memorize a binary configuration, we hope that we'll create a new energy minimum. So we might have our state space for all the states of the net being depicted horizontally here, and the energy being depicted vertically, and we might have one energy minimum for the blue pattern and another for the green pattern. But if those two patterns are nearby, what will happen is we won't get two separate minima. They'll merge to create one minimum at an intermediate location, and that means we can't distinguish those two separate memories, and indeed we'll recall something that's a blend of them rather than the individual memories. That's what limits the capacity of a Hopfield net, that kind of merging of nearby minima. One thing I should mention is this picture is a big misrepresentation. The states of a Hopfield net are really the corners of a hypercube, and it's not very good to show the corners of a hypercube as if they were a continuous one-dimensional horizontal space. One very interesting idea that came out of thinking about how to improve the capacity of a Hopfield net is the idea of unlearning. This was first suggested by Hopfield, Feinstein and Palmer, who suggested the following strategy. You let the net settle from a random initial state, and then you do unlearning. That is, whatever binary state it settles to, you apply the opposite of the storage rule. I think you can see that with the previous example, that red merged minimum, if you let the net settle there and did some unlearning on that merged minimum, you'd get back the two separate minima, because you'd pull up that red point. So by getting rid of deep spurious minima, we can actually increase the memory capacity. Hopfield, Feinstein and Palmer showed that this actually worked, but they didn't have a good analysis of what was really going on. Francis Crick, one of the discoverers of the structure of DNA, and Graham Mitchison proposed that unlearning might be what's going on during REM sleep, that is, rapid eye movement sleep. So the idea was that during the day you store lots of things and you'll get spurious minima. Then at night you put the network in a random state, you settle to a minimum, and you unlearn what you settled to. And that actually explains a big puzzle. This is a puzzle that doesn't seem to puzzle most people who study sleep, but it ought to. Each night you go to sleep and you dream for several hours. When you wake up in the morning, those dreams are all gone. Well, they're not quite all gone. The dream you had just before you woke up, you can get into short-term memory and you'll remember it for a while. And if you think about it, you might remember it for a long time. But we know perfectly well that if we'd woken you up at other times in the night, you'd have been having other dreams. And in the morning, they're just not there. So it looks like you're simply not storing what you're dreaming about. And the question is why? In fact, why do you bother to dream at all? Dreaming is paradoxical in that the state of your brain looks extremely like the state of your brain when you're awake, except that it's not being driven by real input. It's being driven by a relay station just after the real input called the thalamus. So the Crick-Mitchell theory at least explains functionally what the point of dreams is. It's to get rid of those spurious minima. But there's another problem with unlearning, which is a more mathematical problem, which is how much unlearning should we do? Now, given what you've seen in this course so far, a real solution to that problem would be to show that unlearning is part of the process of fitting a model to data. And if you do maximum likelihood fitting of that model, then unlearning will automatically come out of fitting the model. And what's more, you'll know exactly how much unlearning to do. So what we're going to try and do is derive unlearning as the right way to minimize a cost function, where the cost function is how well your neural net models the data that you saw during the day. Before we get to that, I want to talk a little bit about ways that physicists discovered for increasing the capacity of a Hopfield net. As I said, this was a big obsession with the field. I think it's because physicists really love the idea that math they already know might explain how the brain works. That means postdoctoral fellows in physics who can't get a job in physics might be able to get a job in neuroscience. So there were a very large number of papers published in physics journals about Hopfield nets and their storage capacity. Eventually, a very smart student called Elizabeth Gardner figured out that there was actually a much better storage rule if you were concerned about capacity, and that it would use the full capacity of the weights. And I think this storage rule will be familiar to you. Instead of trying to store vectors in one go, what we're going to do is we're going to cycle through the training set many times. So we lose our nice online property that you only have to go through the data once, but in return we're going to gain more efficient storage. What we're going to do is we're going to use the perceptron convergence procedure to train each unit to have the correct state given the states of all the other units in that global vector that we want to store. So you take your net, you put it into the memory state you want to store, and then you take each unit separately and say, would this unit adopt the state I want for it given the states of all the other units? If it would, you leave its incoming weights alone. If it wouldn't, you change its incoming weights in the way specified by the perceptron convergence procedure. And notice those will be integer changes to the weights. You may have to do this several times, and of course if you give it too many memories, this won't converge. You only get convergence with the perceptron convergence procedure if there is a set of weights that will solve the problem. But assuming there is, this is a much more efficient way to store memories in a Hopfield net. This technique has also been developed in another field, statistics, and statisticians call the technique pseudo-likelihood. The idea is to get one thing right given all the other things, and so with high-dimensional data, if you want to build a model of it, the idea is you build a model that tries to get the value on one dimension right given the values on all the other dimensions. The main difference between the perceptron convergence procedure as it's normally used and pseudo-likelihood is that in the Hopfield net the weights are symmetric, so we have to get two sets of gradients for each weight and average them. But apart from that, the way to use the full capacity of a Hopfield net is to use the perceptron convergence procedure and to go through the data several times. In this video, I'm going to explain a very different way of using Hopfield's energy function. We add some hidden units to the network, and what we try and do is make the states of those hidden units represent an interpretation of the perceptual input that's shown on the visible units. So the idea is that the weights between units represent constraints on good interpretations. And by finding a low energy state, we find a good interpretation of the input data. Hopfield nets combine two ideas. The idea that you can find a local energy minimum by using a network of symmetrically connected binary threshold units, and the idea that these local energy minima might correspond to memories. There's a different way of using the ability to find local minima. Instead of using the net to store memories, we can use it to construct interpretations of the sensory input. So the idea is that we have the input represented by some visible units, and we construct an interpretation of that input in the set of hidden units. So the interpretation or explanation of the input is going to be a binary configuration over the hidden units. The energy of the whole system will represent the badness of that interpretation. So to get good interpretations according to our current model of the world, which is in the energy function, we need to find low energy states of the hidden units, given the input represented by the visible units. I want to give an example of this to make the idea clearer. In order to give the example, I need to go into a little bit of detail about what you can infer when you see a 2D line in an image. What does that tell you about the three-dimensional world? So a 2D line in an image could have been caused by many different three-dimensional edges in the world. If this blue dot is your eyeball, and the red lines are two lines of sight coming from the centre of your eyeball, then the black line is a possible 3D edge that would lead to a two-dimensional line on your retina. Here's another 3D edge that would lead to exactly the same thing on your retina. And here's another one, and here's another one. All of these different 3D edges have exactly the same appearance in the image. That's because we've lost the information about how far away the ends of the line are along that line of sight. We know the end is somewhere along the line of sight, but we don't know the depth. So if we assume that a straight 3D edge in the world is the cause of a straight 2D line in the image, then we've lost 2 degrees of freedom of that 3D edge, its depth at each end. So there's a whole family of 3D edges that all correspond to the same 2D line. You can only see one of these 3D edges at a time because they all get in the way of each other. So now we're in a position to see a little example of what you might be able to do if you can use the fact that you can find low energy states of a network of binary units to help you find interpretations of sensory input. So here's the example. We imagine we see a line drawing and we want to interpret it as a three-dimensional thing. So the data we have, let's suppose, is a bunch of 2D lines, like the lines shown in the picture. And for each possible line, we will have set aside a neuron. Don't worry for now about the fact that that would require too many neurons. So for every possible 2D line, we have a neuron. In any one picture, only a few of the possible lines will be present, and so we'll activate just a few of those neurons. So I've shown 2 edges in that picture, activating 2 of the neurons. And those are neurons that represent 2D lines. They're the data. Now, what we're going to do is have a whole bunch of 3D line units, one for each possible 3D line or 3D edge. So each of the 2D line units could be the projection of many different possible 3D lines. We therefore need to make the 2D line unit excite all those 3D lines, but we also need to make them all compete with one another, because you can only see one of them at a time. So here's an example where I have a stack of 3D line units. The green connections are excitatory connections coming from the 2D line unit, all of them with equal weights, saying if this line unit is present, I'm going to try and turn on all of those. But in addition, we need competition between those so that only one of them will turn on, and that's what the red lines represent. And we do that for each 2D line unit. So I'm just showing it to you for the 2D line units that happen to be active at present. And again, don't worry about the fact that this would need far too many units. Now the story is not quite complete. We've now wired into the neural network the information about projection that I showed on the previous slide, i.e. the neural network in those green and red connections understands that each 2D line can correspond to many different 3D edges, but only one of them should be present at a time. But now we know a lot about how 3D edges connect. For example, when we see two 2D lines connect in the image, we think it's almost certain they correspond to edges that have the same depth at the point where the lines connect. So let's suppose that the two 3D edges I've joined there correspond to having the same depth at the point where the two 2D lines join. That means they should support each other. It doesn't have to be like that. You could have a very funny viewpoint where one line ends at a different depth from the other, and you just happen to be at the viewpoint from which they coincide on your retina. But that's very unlikely. So we're going to need to use the fact that we expect 2D lines that coincide in the image to correspond to 3D edges that agree on the depth at that point. So we'll put in a lot of connections like that. But there's an even stronger fact we can use, which is that in our manufactured world, we expect that quite often 3D edges will join in a right angle. And so for two particular 3D edges that happen to agree in depth and join at a right angle, we'll put in a particularly strong connection. And I've indicated that by a thicker green line. So by putting in lots of connections like that, we can indicate how we expect 3D edges to go together to form a coherent 3D object. And now we have a network that contains information about how edges go together in the world and about how edges project to cause lines in the image. And so if we give that network an image, it should be able to come up with an interpretation of the image. And for the image I'm showing you, there's two quite different interpretations. It's called a Necker cube, and if you look at it long enough, it will flip in depth on you. And this network would have two pretty much equally deep energy minima that correspond to those two interpretations of the Necker cube. Remember, this is all just an analogy so you understand the idea of using low energy states as interpretations of perceptual data. To actually build a proper model of what happens when the Necker cube flips would be a lot more complicated than this. So if we decide we're going to use low energy states to represent good perceptual interpretations, then we have two issues. The first is to do with search, and I'm going to deal with that in the next video. The search question is, how do we avoid the hidden units getting trapped in poor local minima of the energy function? The poor minima represent interpretations that are suboptimal given our current model in the weights of the network. Can we do anything better than simply going downhill in energy from some random starting state? The second issue, which seems even more difficult, is how do we learn the weights on the connections between hidden units and between visible units and hidden units? Is there some simple learning algorithm for adjusting all those weights so that we get sensible perceptual interpretations? And notice here we haven't got a supervisor anywhere. We're just showing it input, and we'd like it to construct patterns of activity in the hidden units that represent sensible interpretations. This seems like a rather tall order. In this video, I'm going to explain how adding noise can help systems escape from local minima, and I'm going to show what you have to do to the units in a Hopfield net to add noise in the appropriate way. I'm now going to introduce the idea that we can find better minima by using noise. So a Hopfield net always makes decisions that reduce the energy, or if it doesn't change the state of a unit, the energy stays the same. This makes it impossible to climb out of a local minimum. So if you look at the landscape here, if we get into the local minimum A, there's no way we're going to get over the energy barrier to get to the better minimum B, because we can't go uphill in energy. If we add random noise, we can escape from poor minima, especially minima that are shallow, that is, ones that don't have big energy barriers around them. It turns out, rather than using a fixed noise level, the most effective strategy is to start with a lot of noise, which allows you to explore the space on a coarse scale, and find the generally good regions of the space, and then to decrease the noise level. With a lot of noise, you can cross big barriers. As you decrease the noise level, you start concentrating on the best nearby minima. If you slowly reduce the noise so that the system ends up in a deep minimum, that's called simulated annealing. And this idea was propagated by Kirkpatrick at around the same time as Hopfield Nets were proposed. So the reason for simulated annealing is because the temperature in a physical system, or in a simulated system with an energy function, affects the transition probabilities. So in a high temperature system, the probability of going uphill from B to A is lower than the probability of going downhill from A to B, but it's not much lower. In effect, the temperature flattens the energy landscape. And so the little black dots are meant to be particles, and what we're imagining is particles moving about according to the transition probabilities that you get with an energy function and a temperature. And this might be a typical distribution if you run the system at high temperature, where it's easy to cross barriers, but it's also hard to stay in a deep minimum once you've got there. If you run the system at much lower temperature, then your probability of crossing barriers gets much smaller, but your ratio gets much better. So the ratio of the probability of going from A to B versus the probability of going from B to A is much better in the low temperature system. And so if we run it long enough, we would expect all the particles to end up in B. But if we just run it for a long time at low temperature, it will take a very long time for particles to escape from A. And it turns out a good compromise is to start at a high temperature and gradually reduce the temperature. The way we get noise into a Hopfield net is to replace the binary threshold units by binary stochastic units that make biased random decisions. And the amount of noise is controlled by something called temperature, which you'll see in a minute in the equation. Raising the noise level is equivalent to decreasing all the energy gaps between configurations. So this is our normal logistic equation, but with the energy gap scaled by a temperature. If the temperature is very high, that exponent will be roughly 0, so the right-hand side will be 1 over 1 plus 1, and so the probability of the unit turning on will be about a half. It'll be in its on and off states more or less equally often. As we lower the temperature, depending on the sign of delta E, the unit will either become more and more firmly on or more and more firmly off. At 0 temperature, which is what we're using in a Hopfield net, then the sign of delta E determines whether the right-hand side goes to 0 or goes to 1. But with T0, it'll either be 0 or 1 on the right-hand side, and so the unit will behave deterministically, and that's a binary threshold unit that will always adopt whatever of the two states is the lowest energy. So the energy gap we saw on a previous slide, and it's just the difference in the energy of the whole system depending on whether unit I is off or whether unit I is on. Although simulated annealing is a very powerful method for improving searches that get stuck in local optima, and although it was influential in leading Terry Sinofsky and I to the ideas behind Boltzmann machines, it's actually a big distraction from understanding Boltzmann machines. So I'm not going to talk about it anymore in this course, even though it's a very interesting idea. And from now on, I'm going to use binary stochastic units that have a temperature of 1. That is, it's the standard logistic function in the energy gap. So one concept that you need to understand in order to understand the learning procedure for Boltzmann machines is the concept of thermal equilibrium. And because we're setting the temperature to 1, it's the concept of thermal equilibrium at a fixed temperature. It's a difficult concept. Most people think that it means the system has settled down and isn't changing anymore. That's normally what equilibrium means. but it's not the states of the individual units that have settled down. The individual units are still rattling around at thermal equilibrium, unless the temperature is zero. The thing that settles down is the probability distribution over configurations. That's a difficult concept the first time you meet it, and so I'm going to give you an example. The probability distribution settles to a particular distribution called the stationary distribution. This stationary distribution is determined by the energy function of the system. And in fact, in the stationary distribution, the probability of any configuration is proportional to e to the minus its energy. A nice intuitive way to think about thermal equilibrium is to imagine a huge ensemble of identical systems that all have exactly the same energy function. So imagine a very large number of stochastic Hopfield nets, all with the same weights. Now in that huge ensemble, we can define the probability of a configuration as the fraction of the systems that are in that configuration. So now we can understand what's happening as we approach thermal equilibrium. We can start with any distribution we like over all these identical systems. We could make them all be in the same configuration. So that's a distribution with a probability of 1 on one configuration and 0 on everything else. Or we could start them off with an equal number of systems in each possible configuration. So that's a uniform distribution. And then we're going to keep applying our stochastic update rule, which in the case of a stochastic Hopfield net would mean you pick a unit and you look at its energy gap and you make a random decision based on that energy gap about whether to turn it on or turn it off. Then you go and pick another unit and so on. We keep applying that stochastic rule, and after we've run the system stochastically in this way, we may eventually reach a situation where the fraction of the systems in each configuration remains constant. In fact, that's what will happen if we have symmetric connections. That's the stationary distribution that physicists call thermal equilibrium. Any given system keeps changing its configuration. We apply the update rule, and the states of its units will keep flipping between 0 and 1. But the fraction of systems in any particular configuration doesn't change. And that's because we have many, many more systems than we have configurations. So here's an analogy, just to help with the concept. Imagine a very large casino in Las Vegas with lots of card dealers. In fact, we have many more than 52 factorial card dealers. We start with all the card packs in the standard order that they come from the manufacturer. Let's suppose that has the ace of spades, then the king of spades, then the queen of spades. And then the dealers all start shuffling. And they do random shuffles. They don't do fancy shuffles that bring them back to the same order again. After a few shuffles, there's still a good chance that the king of spades will be next to the queen of spades in any given pack. So the packs have not yet forgotten where they started. Their initial order is still influencing their current order. If we keep shuffling, eventually the initial order will be irrelevant. The packs will have forgotten where they started, and in fact, in this example, there will be an equal number of packs in each of the 52 factorial possible orders. Once this has happened, if we carry on shuffling, there'll still be an equal number of packs in each of the 52 factorial orders. That's why it's called equilibrium. It's because the fraction in any one configuration doesn't change, even though the individual systems are still changing. The thing that's wrong with this analogy is that once we've reached equilibrium here, all configurations have equal energy, and so they all have the same probability. In general, we're interested in reaching equilibrium for systems where some configurations have lower energy than others. In this video, I'm going to explain how a Boltzmann machine models a set of binary data vectors. I'm going to start by explaining why we might want to model a set of binary data vectors, and what we could do with such a model if we had it. And then I'm going to show how the probabilities assigned to binary data vectors are determined by the weights in a Boltzmann machine. Stochastic Hopfield nets with hidden units, which we also call Boltzmann machines, are good at modelling binary data. So given a set of binary training vectors, they can use the hidden units to fit a model that assigns a probability to every possible binary vector. There are several reasons why you might like to be able to do that. If, for example, you had several different distributions of binary vectors, you might like to look at a new binary vector and decide which distribution it came from. So you might have different kinds of documents, and you might represent a document by a number of binary features, each of which says whether there's more than 0 occurrences of a particular word in that document. For different kinds of documents, you'd expect different counts for the different words, maybe also different correlations between words. And so you could use a set of hidden units to model the distribution for each document. And then you could pick the most likely document by seeing, and then you could assign a test document to the appropriate class by seeing which class of documents is most likely to have produced that binary vector. You could also use Boltzmann machines for monitoring complex systems to detect unusual behavior. Suppose, for example, that you had a nuclear power station and all of the dials were binary. So you get a whole bunch of binary numbers that tell you something about the state of the power station. What you'd like to do is notice that it's in an unusual state, a state that's not like states you've seen before. And you don't want to use supervised learning for that, because really you don't want to have any examples of states that cause it to blow up. You'd rather be able to detect that it's going into such a state without ever having seen such a state before. And you could do that by building a model of what the normal states look like, and then noticing that this state is different from the normal states. If you have models of several different distributions, you can compute the posterior probability that a particular distribution produced the observed data by using Bayes' theorem. So given the observed data, the probability it came from model I, under the assumption that it came from one of your models, is the probability that model I would have produced that data divided by the same quantity for all models. Now I want to talk about two ways of producing models of data, in particular of binary vectors. The most natural way to think about generating a binary vector is to first generate the states of some latent variables, and then use the latent variables to generate the binary vector. So in a causal model, we use two sequential steps. These are the latent variables, or hidden units, and we first pick the states of the latent variables from their prior distributions. Often in a causal model, these will be independent in the prior, so their probability of turning on, if they were binary latent variables, would just depend on some bias that each one of them has. Then, once we've picked a state for those, we would use those to generate the states of the visible units by using weighted connections in this model. So this is a kind of neural network causal generative model. It's using logistic units, and it uses biases for the hidden units and weights on the connections between hidden and visible units to assign a probability to every possible visible vector. The probability of generating a particular vector v is just the sum over all the possible hidden states of the probability of generating that hidden state times the probability of generating v given that you've already generated that hidden state. So that's a causal model. Factor analysis, for example, is a causal model that uses continuous variables, and it's probably the most natural way to think about generating data. In fact, some people, when they say generative model, mean a causal model like this. But there's a completely different kind of model. A Boltzmann machine is an energy-based model, and in this kind of model, you don't generate data causally. It's not a causal generative model. Instead, everything's defined in terms of the energies of joint configurations of visible and hidden units. There's two ways of relating the energy of a joint configuration to its probability. You can simply define the probability to be the probability of a joint configuration of the visible and hidden variables is proportional to e to the negative energy of that joint configuration. Or you can define it procedurally by saying we're going to define the probability as the probability of finding the network in that state after we've updated all the stochastic binary units for enough times so that we reach thermal equilibrium. The good news is that those two definitions agree. The energy of a joint configuration of the visible and hidden units has 5 terms in it. So I've put the negative energy to save having to put lots of minus signs. And so the negative energy of the joint configuration VH, that's with vector V on the visible units and H on the hidden units, has bias terms where Vi is the binary state of the ith unit in vector V, and Bk is the bias of the kth unit, in this case a hidden unit. So that's the first 2 terms. Then there's the visible-visible interactions, and to avoid counting each of those interactions twice, we can just say we're going to count with indices I and j and make sure that I is always less than j. That'll avoid counting the interaction of something with itself, and also avoid counting pairs twice, and so we don't have to put a half in front. Then there's the visible-hidden interactions, where Wik is a weight on a visible-hidden interaction. And then there's the hidden-to-hidden interactions. So the way we use the energies to define probabilities is that the probability of a joint configuration over V and H is proportional to e to the minus VH. To make that an equality, we need to normalize the right-hand side by all possible configurations over the visible and hidden units. And that's what the divisor there is. That's often called the partition function. That's what physicists call it. And notice that it has exponentially many terms. To get the probability of a configuration of the visible units alone, we have to sum over all possible configurations of the hidden units. So P of V is the sum over all possible h's of e to the minus the energy you get with that h, normalized by the partition function. I want to give you an example of how we compute the probabilities of the different visible vectors, because that'll give you a good feel for what's involved. It's all very well to see the equations, but I find I understand it much better when I've worked through the computation. So let's take a network with 2 hidden units and 2 visible units, and we'll ignore biases, so we've just got 3 weights here. To keep things simple, I'm not going to connect the visible units to each other. So the first thing we do is write down all possible states of the visible units. I'm going to put them in different colours, and I'm going to write each state 4 times, because for each state of the visible units, there's 4 possible states of the hidden units that could go with it. So that gives us 16 possible joint configurations. Now, for each of those joint configurations, we're going to compute its negative energy, minus E. So if you look at the first line, when all of the units are on, the negative energy will be plus 2 minus 1 plus 1 is plus 2. And we do this for all 16 possible joint configurations. We then take the negative energies and we exponentiate them. And that will give us unnormalized probabilities. So these are the unnormalized probabilities of the configurations. Their probabilities are proportional to this. If we add all those up to get 39.7, and then we divide everything by 39.7, we get the probabilities of joint configurations. There they all are. Now, if we want the probability of a particular visible configuration, we have to sum over all the hidden configurations that could go with it. And so we add up the numbers in each block, and now we've computed the probability of each possible visible vector in a Boltzmann machine that has these 3 weights in it. Now let's ask how we get a sample from the model when the network's bigger than that. Obviously in the network we just computed, we can figure out the probability of everything because it's small. But when the network's big, we can't do these exponentially large computations. So if there's more than a few hidden units, we can't actually compute that partition function. There's too many terms in it. But we can use Markov chain Monte Carlo to get samples from the model by starting from a random global configuration and then picking units at random and updating them stochastically based on their energy gaps. Those energy gaps being determined by the states of all the other units in the network. If we keep doing that until the Markov chain reaches its stationary distribution, then we'll have a sample from the model. And the probability of that sample is related to its energy by the Boltzmann distribution. That is, the probability of the sample is proportional to e to the minus the energy. What about getting a sample from the posterior distribution over hidden configurations when given a data vector? It turns out we're going to need that for learning. So the number of possible hidden configurations is again exponential. So again we use Markov chain Monte Carlo. And it's just the same as getting a sample from the model, except that we keep the visible units clamped to the data vector we're interested in. So we only update the hidden units. The reason we need to get samples from the posterior distribution given a data vector is we might want to know a good explanation for the observed data, and we might want to base our actions on that good explanation, but we also need to know that for learning.